Time to come up with the specific equations for each type of collision. But first, let's talk about how we found this out. Measurements. During a collision or an explosion, measurements taken show that the total momentum of a closed system does not change. So not only is that the theory, it's been experimentally proven over and over and over again. The way we're going to show this is we're going to have an object here, object A, object B. We're going to choose to the right to be our positive x, and we'll show the momentum of each object as m sub A v sub A or mb v sub B. And by the way, there's nothing magic about these subscripts. As a matter of fact, later on we're going to move to numbers. They collide. That's what this picture shows. They then move away. We're not being too careful about the length of the vectors because we don't know yet which will have the which momentum goes with which object. We'll need the equation. But the key point here is this little thing here, the prime. That shows the velocity after the collision. And the advertisement over here for basically physics in general, if the measurements don't show something, then it's not a good law, it's not a good theory. Fortunately for us on conservation of momentum, the experiments bear out what the predictions say. We're going to save a little time here. Since we know that velocity is a vector, we're going to leave off the arrows. I mean, to be totally correct here, over every velocity we should have an arrow. But we're only dealing in one dimension, so we know the direction is either going to be right or left. And if you're going to the left, we'll put a negative sign in front of the momentum. If you're going to the right, we'll put a positive. When you work in multi-dimensions, then it's more important to keep the vector sign. But for now, we'll leave it out. So our equation, in this case, for an inelastic collision, or actually any collision, sorry, will be right here. And this is the equation we're going to modify for the specific types of collisions. So you have the initial condition here, MAVA plus MBVB, and we have the same thing on the right side with the addition of this little prime sign, which tells you that that's the velocity after the collision or explosion. In a perfect inelastic collision, two objects collide and stick together, moving afterwards as one object. We talk a lot about two objects colliding. That's because we can solve for that pretty exactly, and it models what happens in the real world. Once you get three objects, all bets are off. The math is horrible, it's very sensitive to your initial conditions and what happens during the collision, and we just can't come up with a good answer. However, for two, it works perfectly. Physics and the real world can be funny like that. So in this case, we have an initial momentum of sphere A and B, and then we have a final momentum of both of them. We have an isolated system, so momentum is conserved. The left-hand side of the equation is what we've done already. But the right side, we now only have one object with a combined mass of MA plus MB, and they move together because they're one object. So we have V prime. That's the final velocity of the joined object.